Let's now calculate the heat rate when we consider the fins. The section will look like this. So we have the plain wall, and now we have to add the different fins. The dimensions of the fins are T is equal to the thickness 125 millimeters, and the length of the fin is 2.5 centimeters. First of all, we need to know how many fins we have. So this is the plain wall from a different perspective. It's 1 by 1. We know that the thickness of the different fins is 1.25. So this is 125 millimeters, and they are separated 2 centimeters. So the number of fins that we can place on this size of the plane is equal to 100 centimeters, which is 1 meter, over 2 centimeters, and this is equal to 50. So we have 50 fins in total. In order to calculate the area of the fins, and also the area of this element without the fins, that is a sub 0, we also will need the help of this diagram. So the area a sub 0 is equal to the total area minus 50 fins times the area, the cross-sectional area of the fins. This is equal to the total area 1 square meter minus 50 times the cross-sectional area of the fin, which is equal to 1 meter times the thickness 125 times 10 minus 3 to convert from millimeters to meters. This is equal to 0.9375 square meter. What about now the area of the fins? A sub F. This is equal to the number of fins, which is 50, times the perimeter, which would be here, times the length of the fin. So 50 times the perimeter times the L of the fin. This is equal to 50 times the perimeter here is equal to 2 times the thickness plus 2 times the width of the plane. And the length is 2.5 centimeters. So this is equal to 50 times 2 times the thickness, 125 millimeters time minus 3 times 2 the width of the plane, which is 1 meter, times 2.5 10 minus 2 meter centimeter. You make the calculations, and this is equal to 2.5 square meter. We are going to be using the electrical circuit analogy as well here to calculate the heat rate. And if we draw a diagram of the different thermal resistances, it would be the resistance due to the convection in the water side, resistance due to conduction through the plane wall, and then we have a combination of the different thermal resistances due to the fin. We can call this one R3 prime and this one R4, and this will be the total heat rate transfer when we have fins. We can call Q2. This combination of resistances here, we can call it R5. So R1, R2 and R5 are in series, while R3 prime and R4 are in parallel. That means that 1 over R5 is equal to 1 over R3 prime times 1 over R4. R3 prime is equal to the 1 over the convective heat transfer coefficient times the area. So the inverse of that will be HA, because it's on the air side, times E sub 0, times plus the inverse of the R4, which is directly related to the fin, the convection happening in the fins. This is equal to H in the area, in the air side, times the area of the fin times the efficiency of the fin. Therefore, R5 is equal to 1 over HA times A sub 0 plus HA times the area of the fin times the efficiency of the fin. We know that the heat transfer coefficient in the air side is equal to 15 watt square meter Kelvin. H0 we just calculated and it was 0.93575 square meter. The HA can be, we can use HA here as well. So we have now HF, so that's the area of the fin, which is equal to 2.5 square meter times the efficiency. So we need to calculate the efficiency. In order to calculate the efficiency, we are going to be using this graphical method that we saw during the presentations. We have something like a graph like this one, when we have on the y-axis the efficiency and the x-axis a parameter which is equal to the length of the fin square root of h over the thermal conductivity times the thickness, half of the thickness of the fin. We have some lines here, if you remember, some curves here, and we have to take this one when the radius is a flat fin. Okay, so let's calculate this parameter here. L is the length of the fin, which is equal to 2.5 centimeters times 10 minus 2 meter centimeter, square root of the convective coefficient in the air side is 15 watt square meter Kelvin, over the thermal conductivity 45.1 watt meter Kelvin times T. But if you remember here, the thickness is defined as 2T. That means that we need to use the half of the thickness. 125 over 2, 10 minus 3 millimeter. You make the calculations and the value of this parameter is 0.576. So if you get with this value in the graph, you will have something like here, and it's a very high efficiency. It's 0.95. So now we can use this value of the efficiency to calculate the resistance R5. This is 0.95. And therefore the value of the resistance is 0.02 Kelvin watt. So now we know the value of the resistance on the water side, the resistance due to the conductivity, and also the resistance due to the fin. We just need to use the general formula. Q2 is equal to delta T over the sum of the resistances R1, R2, R5. Delta T over R1, which is 0.004, times R2, which is 0.123, 4 zeros, 65, plus R5, which is 0.02 kilogram watt. And you made the calculations, and this is 41.34 delta T. Therefore, the relationship between Q2 and Q1 is equal to 41.34 delta T, and Q1 from the first section, we know that is 14.13 delta T. Therefore, the heat rate when we consider fins is 2.92 times higher than the heat rate without considering any fin. So you can see there is a huge improvement in